slowly start with our final lecture. And so thank you for coming, and thank you for surviving over these 5 days. I hope at least some of you are still standing or sitting or whatever is the... So last time we finished this rainbow cycle, and we kind of went in quite a lot of detail through it to showcase various things you kind of need to do when playing with these things. So for today, and what we started a bit last time, is how we can also use decompositions. So for problems in which you aren't just looking for a single object so that you can just pass into expander, but you're looking for trying to do something more complicated that involves your whole big initial graph, so that this can still be useful when working with this type of problems. So I wrote this slightly tweaked version of expansion. It's actually pretty similar to what we had before. I just dropped the dependency on the size of the sets we're expanding, just because it makes things cleaner. If you wish, you can prove this lemma with some such dependency, but it will kind of by default be a bit worse than what you get with just pass to expander lemmas. And I don't really know to decompose into these old robust sublinear expanders. So twofold thing, we need something weaker, and then it becomes less kind of crucial to try to optimize everything because it's possibly not even tight. So I do know how to get better if you are willing to give me here more than n. So if you give me here like n polylog n, then I can decompose in better expanders. But so there is some trade-offs you can still play depending on what your problem actually wants. So then I stated this decomposition lemma, which just says that any graph, you can partition its edge set into a few edges, which we kind of think of as discarded or rubbish, and so that we will not use. And the rest, so most of the graph, we decompose into expanders like that, where the expansion factor is 1 over log squared. And the edge robustness factor comes from how many edges you were willing to discard. If you're not willing to discard any edges, you don't get any robustness, but you can still decompose into such things. So actually, there is an exercise in the notes that's asking you to kind of use this lemma to show that actually you can find in any graph, so even at large constant degree, you can find one of these sublinear expanders with 1 over log squared expansion. So, but no robustness. And you can use this end average degree being, let's say, half of the original or something like that. So this gives you a version of this Komlós and Szemerédi pass to expander type things, but kind of just as a corollary of this type of decomposition lemma. And I'll soon say just a word why that happened here and why this lemma works better than what we were doing before for this type of cases. So for the proof, I wrote on the board how it works to save some time, and I don't really want to go in great detail through it because it's essentially the same proof as we've seen for the pass to expander lemma. We're just doing this slightly different variant of that approach where we are kind of doing the algorithmic version of finding a sparse cut and iterating on the pieces that cut separates. So formally, kind of how to implement this is you run an induction on n. Basis is something trivial to check. Let's not worry about that. You do need to usually worry about that, but let's not worry about that. So if G is already an expander, we're done. We see it's a decomposition in itself. Otherwise, there is a U and F which fail the expansion condition. Discard the edges in F. This will go into our junk set. And then invoke induction on the 2 graphs that we looked at for the pass to expander lemma as well, right? The set that doesn't expand well anymore, plus its small neighborhood, and the complement, right? And then induction gives you 2 decompositions, one of each of these graphs. And so technically, I think here I need to decide where I put edges, because before we could do them wherever, but if we all want a decomposition, and there are some edges that live both here and here, so I choose that they live in one or the other so that we get the perfect decomposition, but let's not worry too much about that. Then, so we apply induction, we get these decompositions, and we just jumble them together. So that's really the whole process. So now the rest is just checking that things work out. So the first check is that you did not drop too many edges. There are 3 sets of edges that you dropped: induction application on H1, induction application on H2, and F. And if you write down what this is, it will look exactly the same as the computation we did some time ago for this path-to-expander lemma for the robust sublinear expanders. Even the exact function n log n shows up. So this is actually even easier here because you don't have the dependency on u. So it's just really the kind of worst case of that one that you just need to do. Second one is something we didn't have there, and this is something that we want to use to control the total number of vertices that you use. So again, this one uses that number of vertices on the left. This one uses also that number of vertices on the left. And now you realize that actually this one is n1, this one is n2. So it's 2n1 plus 2n2. But I'm lying, that's not smaller than 2n, right? Because n1 actually had a few extra vertices that we used in this like neighborhood of, right? So this has size n1. This has size, n1 is u plus epsilon times u, right? So, and this is n minus u. So actually the number of vertices is a bit bigger. So what you need to do to get this to work is actually just improve the statement a bit and put here 2n over 2 plus log n. So this is this curious phenomenon that when you're doing induction, you actually want to prove the kind of as strong a statement as you possibly can because it makes your induction assumption stronger. So if you add this, and if you analyze what happens there, you'll see that it precisely gives you a little bit of extra gain. And actually, this tweak is the kind of difference that actually lets you find even sublinear expanders in constant degree. So this a similar feature actually appears for the Komlós and Szemerédi. They do it a bit in a different way, but somehow this extra thing that seems to make the problem harder actually makes it easier for you. So again, I mean, this, how do you find this? I don't really have time, but you write down a recursion. F of n is the function I want to work with. I want f of n1 plus f of n2 to do this. And then you play with this function, and you figure out what sort of thing you actually are aiming for. Very good. So I will leave the computations to you. They are written out in the notes if you want to read them carefully, I hope. And, but I don't want to spend more time on the actual proof of the decomposition. And let's actually try to use it once or twice. Any questions? OK, very good. So the application is going to be to some classical sparse decomposition problems. And actually, if you maybe went to the talk of Maya yesterday, it's actually kind of closely related to what she was talking about, but somewhat different problem. But similar ideas go between these two. So let me start with theorem of Lovász, which is sort of, I think, the main result and the most used result in these sparse decomposition theorems, because quite a lot of them actually just use this as a black box. And for me, by sparse decomposition, I mean I'm decomposing into paths and cycles, but you can do some similar stuff with forests, etc. It becomes different, but so sparse means paths and cycles. Very good. So, so what he proved is that any graph on n vertices can be decomposed, and I always mean edge decompositions. So this I said last time, and I will not be writing it, but I do mean it. Can be decomposed into at most floor of n over 2 paths and cycles. So this is tight. It's not too hard to see if you take a complete graph, and there are other tight examples. It's so really tight, not even up to constant factor, but really perfect answer. The proof is a kind of a beautiful induction argument that is, though, very delicate. So if you want to kind of tweak this proof, it starts not working, usually. But despite that, so people usually use it as a black box. So let me follow that. Pattern. So, so here's the corollary. So we can decompose into paths such that every vertex is an endpoint of at most 2. So if you think about it, that will tell you you have at most n paths. We can decompose into fewer paths, but actually this sort of spread around property of endpoints is going to be more useful to us than actually getting a better path decomposition. So this result has been really used for settling quite a few related problems, and I would actually be very curious in seeing a different proof than this induction one that Lovász had from the 60s, and just because precisely there are a few problems where it doesn't work out because it's in some sense delicate, and one of those we are going to talk about today. So I'm not going to prove the corollary. I leave it as an exercise for you because it's slightly off topic, but it's actually a cute one paragraph, one idea argument. So and it's very, very nice, but in the interest of time, I'm not going to do that. So I also put in the notes the problem to try to prove a covering version of Lovász. So for that, I know a kind of simple, nice argument, and this is actually something that Maya mentioned. One of the results that she mentioned yesterday sort of does that along the way. So it's very nice, clean, and versatile, but what it does is it covers, it doesn't decompose. It reuses some edges between the paths. So that usually makes these questions much easier, and it's, well, much is a strong word. It's still like the conjectures took about 30 years to get resolved, but they are resolved, unlike the decomposition ones, which still stand. So the main one that I want to talk about is a conjecture of Erdős and Gallai from the 1966. So it preceded this Lovász paper, so this was, I think, a bit in response to that paper because they asked several questions, but that has been some time ago now, so let me put 66. Show that any n-vertex graph can be decomposed in big O of n cycles and edges. So in that paper, they called edges cycles of length 2. So if you read it, they will just tell you decompose it into cycles, and then you wonder, wait, what if it's a forest, or what if it's a tree? How am I going to decompose it? And then you need to read that there is somewhere a comment that, for the purposes of this. They don't state it that way, but that they treat edges as cycles of length 2. So precisely, like if you don't have any cycles, you can't decompose. And actually, it's equivalent to saying that every graph with all even degrees can be decomposed into cycles. Because as soon as you have an odd degree, that means you will not be able to do it. But when they're all even, then you can just use cycles. And it's not too hard to show that proving that you can do that in linearly many cycles and with cycles and edges is the same. But actually, for us, it's more convenient to have also this extra freedom on the edges when working on it. Very good. So it's a very nice old problem, and let me tell you what we know. And also, somehow it looks a little bit unrelated to any of these things, right? So how exactly are we going to use the path to expander lemmas to attack that thing, right, if you lose the rest of the graph? So this is why decomposition lemmas into expanders work much better for this. So let me keep the left board alive. For now, and I'll tell you what we know. So as an exercise for you, prove that you can do it with n log n cycles and edges. So that's, again, in the notes written, but I will not be writing the exercises on the board, mostly because time reasons. But the best known, so there was a result of Komlós, Fox, and Sudakov from 2013, I think. They proved that you can do it with n log log n. So they improved the log n to log log n. And this is, I'm hoping to mostly show that, well, not their argument, but some kind of mix between their argument and the one that came later, but in this class. But the best known bound now is n log star n. So I want to show you kind of a bit of a mix between ideas that go into that and that went into n log log n. So log star is the iterated logarithm function. It's the number of times you need to take a logarithm before the number becomes smaller than 1. So it's this stupidly slowly growing function, which I think at some point someone told me if you plug in the number of atoms in the universe, you get less than 5 or something like that. So it's like super close to a constant, but technically not a constant. So it would be very nice to get rid of it and prove the thing in full. But as far as these asymptotics go, this is, other than inverse Ackermann functions, closest you can kind of get while still not doing it. So I do want to show where kind of where this log star is coming from. So this is a kind of nice reduction, and it will use the decomposition lemma first time, and then we will use it second time to actually prove this intermediate thing. So this comes from the following kind of intermediate theorem, which says that it can be done with big O of n cycles and n times polylog n edges. So it's a sort of asymmetric result which says, okay, if we are willing to pay a bit more edges, then we can actually do it with just linearly many cycles. Okay, so now there is a slight tweak of this. So I will show you how the implications work, and then we will focus just on this result because, or well, analog of it for n log log n. But the basic idea is what you want to do is you want to take your linearly many cycles, remove them out, and notice that your remaining edges make a new graph which now has average degree polylog n. Okay? So we want to apply the same result again to this leftover graph, take out linearly many cycles, and now reduce the average degree to polylog log n. Okay? And keep doing that. And if you think about it, how many of these iterations you need to do, well, it's precisely the log star n, because in the third iteration you are polylog log log, in fourth you are polylog log 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 log, and goes that way. So after log star n many steps, this log 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 nonsense becomes a constant. So you don't care about it anymore. But since you did log star n many times of paying linearly many cycles, you do need to pay the log star n extra to get this. So this is where this magical log star n is showing up here, except what I'm lying to you is that here this only depends on the number of vertices, not on the average degree. So if you technically reapply it, you just again get a polylog and not polylog log. So this is what the theorem 3 does. It just says that you can actually replace this n with the average degree. So it's again, everything is the same, except you get n times log polylog of average degree. Okay, so first I want to show you that theorem 2 implies theorem 3, and then that, so actually I more or less already told you that, so let's just do that first. The theorem 3 implies theorem 1. So proof of theorem 3 implies theorem 1, right, is, so apply theorem 3, remove big O of n cycles, and what happens to average degree? It started as d, and it went to polylog d. by paying linearly many cycles. So now you repeat it to your new graph with polylog d degree. It will again cost you linearly many cycles to go to poly. So now we get 2. And you keep doing that. If you do it log star n many times and you spend 5 minutes thinking about how this log star behaves, you realize that it doesn't really care about the power of this, because as soon as you do another log, this big O of 1 goes in the front, and the next one, it even becomes a constant. So if you can iterate these things, you completely don't care about the power of the log happening there. I mean, it goes hidden in the constant there. So repeat big O of log star d many times. So also technically the main theorem, you can have a log star of average degree rather than of n if you wish. But this just goes so slowly that the kind of distinction is sort of silly unless you figure out how to iterate to get the inverse Ackermann. So anyway, so repeat log star n many times. To reduce average degree to a constant. So that means that this leftover graph had big O of n edges, and this we just put into our decomposition, or discard if you want. And since total number of cycles we paid is n times big O of log star, well, big O of n times big O of log star d, which is what we wanted. Right, so if you want to prove this log star n result, it's enough to prove this asymmetric version where we want few cycles, but we are happy with a bit more leftover edges, because we will be able to iterate this on itself. Make sense? Okay, so no decomposition into expanders yet. I promise they will show up. So now let's see why theorem 2 implies theorem 3. So here, let's do a cleaning step. So, okay, so let's fix d, which is the average degree of our original graph. D will not change throughout the process. This is important. Then remove any cycle which is longer than d iteratively. So remove repeatedly cycles of length at least d. Right? So in total, you have n times d over 2 edges. So you can't remove more than n over 2 cycles if you do this. But we are not updating the average degree as we do that. So we just stick with the original one. Okay? So this costs big O, well, actually, at most n over 2 cycles. Okay. The rest of the graph doesn't have long cycles. It doesn't have a cycle of length d, right? So let's now apply our decomposition lemma to it, and actually let's apply the perfect one. So s equals 0. So let me say here, so leftover graph G prime has no cycles longer than d. We will use that in a moment. So now apply composition lemma. With s equals to 0 to this G prime. So what does it give us? It gives us 0 leftover edges, right? No junk because S is 0. So it really decomposes everything. So it gives us G1 up to GT. We have no idea what GT is. But what they do satisfy is that their edges are just a decomposition of our current G prime, right? Because S is 0. What we also know is that they aren't much bigger when you sum up their orders compared to the G or G prime itself. And they are each of them an expander. So each GI is 1 over log squared size of GI. 32, we put there usually 0 expander. So that really means going back to our original definition of just epsilon expansion. So I don't even need to write this. It's just that expander if you go back to the one we started from. OK. Now, if you remember what we did in the first class, we said that any expander has a long cycle. Right? But we said we killed all long cycles. So each GI must have size of GI being less than D log to the 4D, maybe big O. Why? If it had that many vertices, then this find a long cycle in expander lemma would tell you that you have a cycle of length D. We killed all of those. So actually, all of these expanders are small. They are very close to the average degree size, which makes us happy. Why it makes us happy? Well, because we can use, remember, we are assuming that we have theorem 2, which allows us to decompose in terms of the number of vertices instead of average degree. So now you can just use theorem 2 on each of them and put it together, and you're done with the theorem 3 average degree. So here I should say by long cycle in expander lemma. From the first class, and that. OK? So now use theorem 2 to decompose each GI into twice into, well, big O of size of GI cycles and size of GI polylog size of GI edges. Right? The difference between two theorems was just one works with number of vertices, one works with average degree. But now, because of this decomposition, they essentially became the same, at least from what we care about. In particular, that means like what is big O of, so how many cycles we have in total, so total number of cycles. So we just concatenate these decompositions, and I claim that works. So total number of cycles is at most sum of this big O of GI. But our lemma conveniently told us that, right, that their sum is at most linear. So this is still linear in N, which is what we wanted. And the total number of edges, so this is where the control on the size of the expanders will come in. is upper bounded, again, a sum of these things. And now to bound the log of GI, I'm going to plug in that. So polylog of this expression is just a polylog of D. Right? This one just disappears because it's some lower order thing, however you like to think of it. So this is at most the sum GI times polylog D. And let's put star, and let's put star. And now we're done, because again, the sum of these GIs is n, and we wanted precisely a bound of the form n times polylog D. Okay? So what we need to do, and what we'll stare at, is this theorem 2. So let me rewrite it. So actually, any questions before I do that? Yes? Last line. Yeah, above you mean this is just explanation why this is true, you mean? Or yeah, so it says by long cycle lemma in expander, you get this upper bound combined with the upper bound on the longest cycle that you have in the graph. So we killed all cycles longer than D, right? So when we're doing this, there is no longer any cycle of length D or more, because we removed them and we paid them already this n over 2 at the beginning of the process. So we killed all long cycles. So now when you get to these expanders, you actually have control on how big they can be, because otherwise you would get another long cycle. Yeah, this is not very legible, but I concede that point. Yes? So all the big O's here, think of them as 100. Like they will range between 100 and 1,000, and I'm just being lazy with keeping track and changing them all the way.
Let's say you decompose your key into two expanders both for n. Decompose each of them into 100 cycles.
So I agree with you that you need to put correct constants in the big O's everywhere. If you do the general, like so this is this always discussion of whether you get to choose your big O constant or whether it works for some correct choice of big O. People have different preferences. I'm trying to save time, and So you use that they are all small in this polylog step here. Sure. But you have an upper bound on the size of GI here to give you an upper bound on this. But I'm not proving the full result yet, right? I'm just reducing to this n times. Okay. Any other questions? Okay, let's prove the main thing, or prove a slightly different main thing. So theorem 2 prime can be done with big O of n cycles and n to the 2, let's say 13 over 7 edges. Now, you should tell me, well, this looks way worse than the polylog, right? And the reason for that is that I just switched into proving a weaker result. So this, if you repeat the argument I just told you, will give you a log n, an n log n upper bound. So the thing is that here you are reducing your average degree if it was d to the 1 minus epsilon. If you analyze how long this takes to destroy all of your average degree, it will take log n steps. Okay? So I want to prove this because proving a polylog here will definitely not fit in 25 minutes. And this, at least, might give you a kind of a very good picture of how this works. OK? So, and some of the ideas I'm doing here are kind of a mix between the log star result and the log log n result. So some things from the log star clean up the log log n. Some are kind of same as what happened in log log n. Very good. So let's do that. Where am I? Not there. Did that. Didn't do that. Good. So we want that. So here the first step is going to be decompose. So apply our decomposition for the second time. Into 4s times n log n edges. And expanders G1 to GT such that GI is, well, we have this sum of GI is at most 2n, and we have that each GI is 1 over 32 log squared n SRE. Well, I guess I should do here GI. But my immediate next step, so I should also tell you what I pick as S. So with S being, so the total number of edges that we are willing to sacrifice. So, well, we'd want that to show up here, so it should be n to the 1 minus epsilon divided by log n, where epsilon is 1 over 7. So I don't write this nasty 1 over 7s. I will just trail along the epsilons instead. OK. So that means that the number of edges we sacrifice here is n to the 2 minus epsilon. And let me again put a big O here. I don't know. I know people don't like it, but I can do 100 if you prefer big O. But I feel happier with big O. Yes. Very good. So, right. So now the next step, let me just assume, let's log assume t is equal to 1. So our original graph was already one of these expanders. So if you know how to prove the thing for the expanders, you again just put together the expander decompositions. You do exactly the same counting as we did there. Because the sum of the orders is still n, everything works out for you and you're happy. I don't want to do these steps because if I do, then I need to relabel everything and then I always mix up the n and m and you run around. Let's just assume we are already in the expander and let's decompose that. OK? Very good. So what's the strategy? So here we have our expander G, and our goal is to decompose it into few cycles and a few leftover edges, right? So it's a nice expander, so it lets you connect up various things nicely. So, and we also have this black box result that I told you will be a black box result, so of Lovász that we can apply, which lets you decompose it into paths with very few collisions between endpoints. Right, so you decompose into paths, and again, it's edge decomposition, so vertices can intersect, but edges cannot. So apply corollary to Lovász. To get path decomposition. With most 2 endpoint collisions per vertex endpoints at any vertex. Right? So now, of course, like we just decomposed our thing and we got paths and we want cycles, right? But we used up everything from the picture. So what can we do? Well, let's take a step back and let's be a bit more clever and let's actually set aside some part. So this is an idea that is absorption-like, if you wish. So kind of save some nice part of your graph at the beginning so that it can help you at the end, right? So we'll set aside some subset of the vertices U. And how big can we take it so that it doesn't hurt us at any point? Well, if you take it to contain at most n to the 1 minus epsilon vertices, then you're happy because the most edges it can ever touch is n to the 2 minus epsilon. So whatever we don't deal with U, we can just discard at the end into our rubbish. Okay? So now we will do LOVAS on the rest of the graph. Okay? And we will use this random subset U to link up the endpoints of the paths into cycles. So that's the strategy we are going to follow. Now, this link up through a random subset needs doing. It's not trivial. I'll get back to it. But let me write set aside U subset of vertices of G such that size of U is at most big O of n to the 2 minus epsilon. Okay? Yes, thank you. Thank you. Right, and now plan link up endpoints of paths via U. So what's the point of U? It makes sure that when you have this path that lived in the complement of U, and when you take this short path that lives for U, it doesn't intersect the path here. So what could have happened, and why we want this random subset, is you have a path here, and now if I just find some path doing, it could be doing something like that. Right? So instead, this is a bad picture, so what instead we are doing is, given this path, given our U, we will immediately jump to U, and then we will walk here, and then we will immediately go back. So that gives us a nice cycle without any issues with going around. So these are all going to be short because we live in an expander. So over the whole process of this n paths that we need to link up, we are not going to use up too many edges that for the previous paths, and we can still avoid them. Again, the problematic business with this is that this is a random subset. It's not an expander itself. This is something we've again seen also in the rainbow cycle, if you remember. Once you start subsampling expanders, you don't inherit expanders. It's hard because union bounds don't work strong enough, so you will not cheaply get an expander. If you did, we would be done at this step in essentially one line. Right? So in expanders, this is like this type of linking business is actually pretty easy if you have a proper expander. You can just chug into the F property whatever you have used up and you don't like being used up. So again, we need to kind of do some acrobatics to deal with the fact that you don't inherit expansion when you sample. So I didn't say it, but kind of a natural guess for the U is you take it at random. Right? So I don't see any smarter way of picking a set U that kind of keeps this sort of expansion properties with respect to the rest of the graph. Right? Because every vertex needs to be able to jump into it, and then inside of it, it needs to shrink compared to the original, but still have this nice linking property. So also, just to point out here that this is actually something that works for log n result. It very much does not work for log star n. Why? Because if you try to do that below n to the 3/2, you have no chance of doing this. If epsilon is a half, and you sample a set of size √n, you don't expect to see any edges inside at all. right? So no linking for u inside there. So here, it's crucial that we're working with the polynomial, and really doing it this way is what makes it maybe doable in the rest 14 minutes that I have left, compared to about 2 lectures that would take me to do the log star n. Okay? I can, if I have, by some miracle, a few minutes at the end, tell you how the actual log star n proceeds, at least at high level. And if not, I gave a 2-hour talk at IAS, actually, so there is a video of that. So if you're interested, you can actually watch that. And you will have seen, actually, decent number of pieces from it. So you can also do it faster than the 2-hour thing. Very good. Right. So our plan is now to sample this u. So sample u as VP. So remember, this was our uniformly independent random sample of, well, every vertex gets sampled with probability p independently. P should be n to the minus epsilon. That's the sort of thing that we can afford to lose. So Chernoff will tell you this is not too big, so this is something we easily ensure. Right, so let me write that. So with high probability, number of edges touching u is smaller or equal than big O of n to the 2 minus epsilon. So we can always discard whatever we don't use. Okay. So the next step, as we said, was to use Lovaas. So use Lovaas. Well, OK, let me not do it yet. I'll do it at the end. But that's morally the next step. Let me now ensure what properties I want from U. So actually, you can prove the desired properties using the sprinkling ideas that I showed you for the colors. So the difference here is that you need to sample vertices instead of colors that we sampled there. And actually, if you think a bit about it, you also realize that you need to sample edges because you need to somehow make sure that they do not reuse edges. So you need to do kind of simultaneous edge and vertex subsampling. It's actually an excellent exercise to run through the sprinkling argument that I showed you. There is one little twist extra that you need to do with the vertex expansion, which is that you do not want to insist that the final vertex is also in the random set. So that's something I always forget, but things break if you don't do it that way. But it's an exercise for you, even in the notes. So what I want to do is I want to show you a slightly different proof, which is based on using something called robust neighborhoods. And this is something that is more used for kind of denser worlds. So when we have this type of expansion, this type of higher degree, and are closer to kind of, or at least a high polynomial or linear degree, and then it works very well. You can also, with modifications, get it to work at sparser things, but there are some trade-offs. So sometimes one looks better, but they are kind of good things for similar problems. So let me show you the other one. You've seen the sprinkling already. So what is a robust neighborhood? So a robust neighborhood of radius 1 around V is just V together with the neighborhood of V. Okay, nothing terribly intelligent happened. So robust neighborhood of radius I around V is just the previous robust neighborhood together with all vertices with at least n to the 1 minus 2 epsilon. I think I need to put maybe here divided by log squared n, not in, what am I doing? Some nonsense like that. Neighbors in the previous robust neighborhood. Let me draw a picture. So we have our current robust neighborhood. So what I want is I want to add only vertices which connect in many ways. Right? So they are kind of hard to disconnect from the previous robust neighborhood. Make sense, the definition? Okay, so now see what's the problem. I have the old notes anyway. So robust. So they have lots of edges going back. So the whole point of this is that it will make it much easier for our vertices to survive this subsampling. Now, what do I mean by that? So I want the following property. I want that for every v and u, which lives in, let's say, ith robust neighborhood of v, but not in the previous one, so it just got added. The number, let's say maybe size of neighborhood of u, when you intersect it with the previous robust neighborhood. Right, so this is the thing that's guaranteed to be at least n to the 1 minus 2 epsilon over log squared n. But now I want to intersect it with our random set u. And I want that this is at least, so what do we expect? Well, this is sampled with probability n to the minus epsilon. So you get n to the 1 minus 3 epsilon things that you expect to see there. So I want this to have with sufficiently high probability. And maybe I need a 4, whatever, so that Chernoff starts to kick in. With probability bigger than 1 minus 1 over, let's say, n cubed or something like that. Right, so that I can ensure that this happens for every v and u. So I guess for a fixed v and u, I want that probability. In total, I want just with high probability. Okay? So this is one property we want from u. The other property is we want that its size kind of behaves correctly. So Chernoff tells you that it's not more than 2 np or less than half np. And the final thing is that we also want that these robust neighborhoods get sampled correctly. So I want that the size of the robust neighborhood of I, so for every v and every I, less or equal than, let's say, log to the 4n. I guess I don't need an upper bound here. The size of the robust neighborhood of radius I around v is at least 0.9 times p times, when we intersect with u, right? I want the random subset is at least 0.9 times p times the size of the actual neighborhood. So these are free pseudo-random properties I want from u. Once I have them, u stops being random. Okay? I fix an outcome of u which satisfies all of these properties. And I claim this lets you link things up. So let me write the claim. for any v, so now fix such an outcome u. I should write that. It's important. It's no longer random. Fix u, fix outcome u. Doing all this. So now I want that for every v and u which live outside of u, outside of big U, there exists a VU. I also want it for every subset of edges which live within U and have size at most n times log to the 4n. So this is the total number of total amount of path length that will accumulate through the process. I'll explain how the claim is applied in a moment, and maybe then leave you to verify that the properties let you do it. So f having that size, there is a VU path of length at most log cubed n, with all internal vertices in U and avoiding edges of F, not using F. Right, so this is the linking property I've been sort of alluding to. If you really can do that, then we're just done in that in the picture, right? Because we have our U, which is nice, has all of these nice properties. We had the path decomposition. We have at most n paths. If we can link up each of them with at most log cubed n edges, going just through U, so you go there, you go there, you go there, you link it, you use up log cubed n edges, then you do another one. In total, you will never use up more than n log to the 4n edges by doing that. So that's what F is there for. And since all the paths go through U, you are happy, and this claim immediately combined with Lova's gives you the decomposition. Okay, now why is the claim true? Well, I claim that these robust neighborhoods actually let you do it. And the reason is that the robust neighborhoods themselves grow exactly the same as if you were the usual expander. So you have 1 over log squared n expansion. So it will take you log cubed n steps to reach more than half. Okay, so one of these things becomes bigger than a half. And I'm guaranteed that a correct proportion of it with respect to U is occupied. So that means that even within U, it will reach more than half, if you think about it for a second. This also uses the upper bound, the control on the size of U that you get from Chernoff. So that means that when you start from any two vertices, you can actually guarantee that there will be a point which intersects in their robust neighborhoods. And now, because we ensured that kind of whichever point you like had enough things surviving going back, you can just backtrack it and find a path that goes back. So that ignores F. And there is one final trick that is important here. And this is that this F has a bit too many edges. It could block out a single vertex, right? So what you want to do is you want to pick this vertex and everyone along a path so that they avoid any vertices which touch too many F edges. So let B be set of vertices in U with at least root n edges of F. Now, the point is you have at most root n roughly of them times some polylog n. And root n is less than n to the 1 minus 3 epsilon because this is 1 over 7. So you can, in each of these steps, avoid going into this B. And now everyone else who is not in B touches at most root n edges of F. So you can also avoid the F edges wherever you are and still have enough things. this was not perfectly put together because it would be nice to have another 10 minutes, but let me stop there and thank you for your attention.